Okay. So the now that everyone who offered to show up has the midterm back. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so still too many people missing. Dang it. All right. For the, I don't really have collective stats on the midterm. Like the whole class is broken down by undergrad and grad. Of course, the undergrads benefited from a undergrad curve. So for the undergrads,
I'm just going to don't ask questions.
Dang it.
Just let me be me.
Okay. I was trying to get like an average or something. Okay. Okay, so for undergrads, the average was a 87, and the high was a 101, achieved by 3 people. Okay. Let's see. Okay. Oh, wait. Sorry, something's wrong here. Okay. Oh, actually, the average is 89. So,
she just became a grad student. She's a new grad.
Yeah.
Yeah.
New baby.
Yeah, just this semester. So.
Yeah. So
Yeah.
sorry, hasn't been long.
Yeah. So he took 460 and 561.
Yeah.
Yeah.
Different place.
So where was that 10-point curve last?
Oh. Okay. Okay. So yeah. So sorry. 89 average for the undergrads. One submission was not included for some
They
reason.
want to know who. If you're an undergrad, please raise your hand. They need to know. They're curious.
Did not make that 101.
Well, actually, there are not many undergrads currently here. There are only 5 undergrads in the room.
Physically right now. And they're always curious.
There are 8 undergrads overall. Where's Sharon? Okay. Okay, and for graduates, okay. The average was 85, and the high was 94. Okay.
I'm excited, girl.
Okay. Now.
2 of those points I lost for silliness. That's just because I was being sassy. Talking about convergence classes.
Oh yeah.
I could have.
Yeah. Well, I think it only cost you 1 point anyway. So.
2.
2.
But
Okay.
I mean, if you want to give me a point,
I think you're good. Yeah. Okay.
my bragging rights.
Yeah. All right. So do we have any questions about the midterm? No. Constant questions were 2 points each. Regular questions were 10 points each.
Can you just tell me 16 and 17?
Okay. Okay. On the concept ones, number 16. If you have a fixed point iteration that diverges, which often happens if g prime at the root is greater than 1 in absolute value. So what you do is you apply the inverse function to both sides. So x equals g of x is equivalent to x equals g inverse of x, and that takes a reciprocal of the slope. So if the old derivative is bad, the new one will be good. So, like I did an example where we had x equals minus ln x, so we changed it to x equals e to the minus x, and it works. Okay,
Wait, can I get what do you want me to write down for that one?
Can you just write on the board what you
That
want
was
us to
a
write?
lot to write down that little bitty space.
And I
well, not really, because I babbled a lot. But
Well,
yeah. So if you have x equals g of x, So this will diverge if G prime at the roots is greater than 1. So what you do is you apply G inverse to both sides. Well, the G and the inverse and the G will cancel. So your new equation is x is G inverse of x. And that would be enough. I was explaining why that works is that the derivative of G inverse is 1 over G prime. So it just flips everything. Okay, that's number 16 in the concept question. And then 17?
Yeah, just because I went stupid
Oh, okay.
in my brain.
Yeah, I think people generally do pretty well in 17. But Newton's normally converges quadratically.
I got that part.
Unless f prime at the root is 0, or if it's very near 0, then convergence slows down to linear. And I didn't even need the linear part, just the circumstance under which it fails to be quadratic is when you have a double root.
Yeah.
Okay. Any other?
Can we do the 2 drawbacks of Newton's method?
On number 18.
Yeah, because I went
Yeah, one thing that was interesting, there were a few questions where I asked for 2 of something, and some of you gave me the same thing worded differently. So when I say the 2 reasons for this, 2 drawbacks of this, I mean distinct. I thought that was kind of implied. So.
My bad.
Yeah, just you have to remember my BS detector is always on. So the drawbacks. First one, you need a derivative, so that's an extra expense. It's the only method of the ones we covered that require a derivative. And then the second one is basically it's unreliable. Or another way to put it, you need a good initial guess. I think most people got this one, or even described it to me twice. Okay. Actually, another question that required 2 of something was earlier. There's number 4. Why pivoting is generally necessary. So one reason was in case you end up dividing by 0, so you can avoid that. The other reason is it reduces round-off error, because round-off error is amplified by the multiplier. Pivoting keeps the multiplier small, so it's not amplified so much. Okay.
And on number 6, could you explain why you can tell it'll converge to something in the matrix? Because I don't.
Oh, for regular problems.
Sorry.
Yeah, it's diagonally dominant. And the Jacobi and Gauss-Seidel are guaranteed to converge in that case. Okay. Like with the Newton's one, yes, they are converging quadratically because f prime is non-zero at the root. Okay. Points were often missed on the fixed point one, showing it has a unique fixed point. I gave a hint, what is the maximum? In the process, you also find the minimum. So the minimum and maximum function on that interval are contained within the interval. G prime is just 2x minus 4, so you can show that on that interval it's between minus 1 and 1. It's actually between plus and minus a half. So that's why that works out. So I think only one person got full credit for that one.
That's 2A.
Yes. Okay. Because a function like this, it's not so hard to see what is the max and min on AB. But okay. Any other questions?
The final example.
Okay. Yes, let's talk about that.
You're welcome.
Okay.
He has big news.
Oh. Okay. 'Cause I started thinking about the material that we're about to cover. I'm going to start today. So rest of the way, it's all about differential equations, so like initial value problems and then boundary value problems. And when I was thinking about what kind of problems I would give for like regular problems, like for an in-class final, I felt that wouldn't work very well. So I'm not going to do that. So here are your options for the final. There's still going to be one. It's just not. It's not going to be like this. So option number 1 is an oral final, which would be comprehensive. So you'd be subjecting yourself to actually
Awesomeness.
what?
Awesomeness.
Okay.
I like your awesomeness.
Like probably about 45 minutes or so of asking questions about anything I've covered. So some of you, well, I guess maybe a few of you who took 460 last semester. Did you do it last? Yeah. Okay. So all right, you can ask her what it was like. Okay.
You know the book, you're good.
Well, I guess you did too, also. Okay. And
did like 3
Karina,
years ago.
you took the oral last. Yeah. Okay. So there are 3 people in this room for sure who took.
Hello.
What?
I
You
did
did
it
it last year.
like 3 years ago though. But I took your oral for numerical 1.
Yeah, but that was different.
Still no exam.
Well, yeah, but.
It's still wonderful.
No, because you were allowed to focus on a particular area. And
Yeah,
I'm not allowing it anymore. So, yes, I'll be asking questions about AX equals B or root finding or differential equations. So, again, studying the quizzes is a good idea. So,
And now the midterm
So for the oral final, it would be like you need to study
book.
the
The book.
The book.
pretty much, yeah,
Oh,
yeah,
okay.
yeah.
Is it kind of that question's like sort of like this?
Like, are we gonna have a conversation, or is it gonna be like strict
Like-
questions?
It's more conversational.
But
But
you don't have to do it in front of everybody, like at least.
It's just you
Yeah,
and
it's
him.
you
and
yeah,
I was really awesome.
so we would figure out a time
Shocker.
either during finals week or it could be the week before, whatever works. Oh, okay, all right. That's, I will not be here. Oh wait, okay. So that time, let me check. Okay, so the last week of classes is
The first weekend of May.
yeah. So it's like April 30th to May
Yes.
4th.
The
Yeah.
fourth.
Oh shoot, I'm not around much of that week. I will be around the Thursday and Friday.
The third and fourth.
The-
Third, fourth.
yes, yeah.
That's good, that's the end of that week.
Yeah.
We have all day books to study.
Yeah. Actually, the third might be your best bet because on the 2nd, like at 11 p.m., I will board a flight from San Francisco to land.
To be delirious.
No,
That's what
it's
you're
coming
telling
back.
us.
It's coming
Well,
back.
yeah, Yeah, to fly from San Francisco to land in New Orleans at 5 in the morning, and then drive up here. So I'll be like
Woohoo.
impaired. So I probably won't, you could probably just say whatever you want and I'll mark it right. So.
Sounds good, like first thing in the morning.
So, okay, that's option number 1. Option number 2, if you like coding, we'll have some basically implementing some of the routines for boundary value problems, which will be among the last things I cover. So it's something I've given before, so I don't have to go to the trouble of making it up. So I'll be posting that pretty soon. Yes, if you've ever had a lot of MATLAB, then it'll be
So like we
yeah.
don't vote, we just get to choose what we
You
want.
pick what you
to
want.
do.
Yeah.
Oh.
Yeah. So it'll be interesting to see how many people choose one option or the other.
I'd have my mallet.
Yeah.
You would choose math.
No, I would have my mallet out to beat people into.
As amusing as that would be. Okay.
Would it not be a typical code they have to go and write or what?
Oh yeah. It's like in any other assignment.
Okay.
Yeah, I'm not gonna make you like do it during 2.5 hours in class or anything.
Oh, yeah, I was like,
You'll have plenty of time
Okay.
for that.
How many questions?
I think
7,
3 or 4. Because what I'm going to put out is I'm going to include a script that will test all your functions. Because I know some of you guys are really bad at testing your code. so
That's going to be 50% of your grade.
so this script will run your code and tell you if the results are accurate or not. And if they are, then great, you can turn that in and you're done. So okay. So I guess you'll have a difficult time choosing which one, because either one would have its appeal to you. But
Well, I might just do both because it's more fun.
oh, okay. Well, alrighty then.
Joking around.
You deserve to do both.
And the 2-hour time limit in the 45 minutes is for the oral exam, and the other hour and 15 is for the format blood test.
Yeah, I like the way this is sounding.
but only for you.
That's just your special numerical cake.
Okay.
Oh, do we get cake?
That's only for
We
calculus.
should have cake.
Sorry, let's all pass and then let's get cake.
Or do you just do that for
Yeah,
Cal
there's
4?
only 2 options.
I've only done it for Cal
2
4.
options? Why are you complaining about 2 options?
Oh, that's you
Huh?
get more
What?
than
Cake?
most
Nothing?
classes.
Just cake? Let's talk about cake.
Cake is way more important. I'd love to make us a cake. What kind of cake do we want?
Strawberry?
Okay. Well, the thing is,
Cream cheese ice?
See?
I need to think about this because to explain for those of you who don't know, when I would teach Calc 4, the last course in the calculus sequence at the last day of class, I'd have a cake with the calculus book imaged onto the cake,
I might have
and the letters no more, so no more calculus. And, so students got to eat their calculus book. And the bakery would even make
There you go.
the sides of the
This is
cake
from mine
like
in
pages.
2014.
I ate my cake and it was so good.
Oh, that's so cute.
I feel like you practiced with our calculus.
I proctored this test last
Yeah.
semester.
Yeah.
I ate like Cheetos and Snickers bar.
Okay. So I'd want to think of
I don't really trust you with my phone.
a good theme for it. So we'll see.
We don't need a same TV wonderful cake.
I know, but well, it's too bad.
You could put no more, what is it, no more errors because you like finalized your book?
Well, the unfortunate thing is, I've tasked my co-author to come up with a cover design.
Yeah, that's not.
Yeah.
And she hasn't done it yet
Oh dear.
because she does some painting as a hobby, and it'd probably be good if she painted something for it. But but she's been busy finishing her PhD. So, but yeah, but actually, no more errors sounds really good because error is such an important concept in this class. So I think you're onto something.
Check
so.
your code.
No more
No more
MATLAB.
errors.
Well,
Check your code.
if Amber never gets to doing the cover, one of my side businesses is graphic design.
Oh, okay.
Doing covers, and I would happily do it for extra credit.
Extra credit.
On top of doing both finals for extra credit?
Yes, exactly.
I would
Which
get extra
says
credit.
far too much
I
about
would
my
get extra
future
credit for that. Okay, so those are the options. Now, as far as if you choose the oral, then you need to talk to me about
I want the oral.
scheduling, just so we can figure it out. Because also, I will not be around on the Monday of finals week. But otherwise, my finals week schedule is pretty open. Like you have a Tuesday, Wednesday, Thursday, so that leaves plenty of time. And actually, if you decide you just want to go ahead and do the code one, it'd be good to let me know because that way that's one less person to think about scheduling. So, but I mean, you have some time to think about which one you want to do. There will be 2 more homeworks. I've posted those on the site already, and that means a grand total of 8 homeworks. The lowest one will be dropped. I know you guys are kind of behind on homework, so yeah, okay. So I've realized that I haven't put up hints for homework 6, so I will put some up tonight because even though the due date for that has already passed, you know how I care about due dates, as in I don't, and only 3 people have turned that in, so out of the class of 17. So okay, so any other questions about anything, like the final, the midterm, whatever? Okay, all right.
Sorry about this cake.
I'm telling you.
Thanks for blurting that out.
I mean, I just realized that this is numerical 2, and when we finished, and I had you for 4, and when we finished, we got cake.
Are we not having class? Are you not gonna be here the first?
I will have a substitute.
Okay.
Is it Amber? No, it's not.
I could.
Ooh, yes, please. Because then I can make goo-goo eyes at her. She's one of my good friends. She's a co-author and one of my friends.
Okay.
Friend
I guess I
Chris.
remember her.
Probably not.
Oh.
She works at
She
William Carey
she
right now.
did one of our D tests for us, didn't she? She gave us one of our D.
No, that was Haley.
That was Haley, I think.
Oh, yeah, it was. Yeah.
She works at William Carey. She
Oh,
should.
Yeah.
Amber. See, here, what's the date? Let me just.
Tuesday, May 1st. Well,
First.
well, I know she's not teaching at that time, but okay.
Tuesday, May.
Oh, because there carries on the trimester there.
Well, she teaches in the morning, so yeah. Okay. Well, let me know how it goes. Well, because when I'm trying to think of who on the faculty I would trust with something from one of my classes, that's kind of
Since it's always a
difficult.
disaster when you have a son.
yeah, it is. So, and then when it's numerical, that narrows it even further, and like, okay. Right. Okay, so you put the question out there.
Aha.
Okay. It's probably kind of funny since I haven't asked her, but okay. Okay. So cool. I can cover stuff.
Okay.
All right.
Who wants to cover?
Although
Ask more questions.
about cake.
I'm serious. This cake thing is really daunting on me. I really like cake.
And the cupcakes are even better because it's like your own individual cake.
And you
But
guys
it's
share
so
it.
small.
It depends on the size of
You
cupcake
just
pan.
get double.
Because I mean, I got some cupcakes.
I mean, I've got some. I can make some pretty big cupcakes.
I mean, when you turn 1, you get that smash cake. Like that's a
We
cupcake.
can each get individual snacks.
And smash our faces in. That'd be fun. It'd be messy. You eat it, girlfriend.
Yeah.
You eat it.
Well, one of my friends got tenure.
You smash cake.
We made her an enormous muffin. Like it was like this big, literally.
Uh-huh.
Because for something that big, you need to have a big treat. So
That's right.
yeah.
What kind of a muffin?
Okay. So now we're moving on to a new kind of problem. So an initial value problem. It has these 2 ingredients. An ODE, or ordinary differential equation. Y prime is some function of t and y. And t goes from some initial time, t naught, up to some final time t. Usually the initial time would be 0, but I'll keep it general here. So it's a general first order differential equation. It may be a system of differential equations, although, will I even get that far? Probably not, but okay. Paired with an initial condition. All right, that is at the initial time of t naught, its value is specified, y naught. Okay, so the 2 of these things together make up an initial value problem. Okay, now, so I want to describe when is it, under what circumstances this problem is well posed. Now, by well posed, I don't know if I've brought this before, but I probably haven't. Meaning that there's three conditions for well posedness, and that is it has a solution, so you have existence, and the solution is unique. And the third condition is that this unique solution depends continuously on the problem data. Now that sounds rather strange. What I mean by that is if you tweak the problem just a little bit, like I might have changed f a little bit or changed y not a little bit, then the solution should not change very much. Now, this concept of depending continuously on data has actually come up before, just not in those terms. So for example, if ax equals b, we want to have a situation where if we change a and b a little bit, or one or the other, the solution x should not change very much. What do we call that? If ax equals b was very sensitive. Yes. So this is a similar idea, that this problem should be well conditioned. So these three conditions together, which are called, those of you who care about some trivia, Hadamard's conditions. Normally for partial differential equations, but they apply just as well to other kinds of problems. So if you have these three conditions, the problem is well posed, which means it's something that is you can solve numerically, because you want to have a solution at all. And this third condition is very important because you can always expect some error in the data. If that little bit of error throws off a solution to a great degree, then it's not a problem that's practical to try to solve numerically. Okay, so we'll be able to give conditions on when this problem is in fact well posed. So
She said yes.
really,
Yeah.
okay, but you wouldn't have even told her, because I haven't told you, what she would be covering.
I told her, well, I told her the whole conversation.
She's like, why are you asking?
And I mentioned all this stuff. Well, what did he say to that? That he trusts you? And he laughed, of course. And that you would find it weird that I was asking not him. To which she said, well, you can tell him that he was right. And then I said yes.
Okay.
And I sent her the salsa dancing girl.
Okay.
A lot of them.
All right. Well, she'd be covering finite difference methods for boundary value problems, so you can tell her
Can you
that.
say that slowly? I got finite.
Finite difference methods
You may have to spell it for me.
Shut
for that was good. Boundary value problems. You know what? After you type out all that, in parentheses put 721. That's the class she took with me last summer, so she's actually seen this stuff.
Does that say when is this problem? Is.
Yeah.
When is? Yeah.
When is this problem?
Is well posed. You've got two ises.
When this
Oh.
problem is.
Yeah.
Oh, okay.
Yeah.
You just had me about
See, and I thought that, but I was just like, I'm just gonna let it slide.
Well, I wasn't sure if it was an S.
Like she made fun of my English.
Okay. So what is this problem posed? So there's a
I didn't need to just
all right. So there's a theorem for this. Okay. So I need to define a domain, which is our interval in time, initial time t naught to final time t, along with the real numbers, which is where y would live. So here we have t and y. So if your function f from the differential equation is continuous on this domain with respect to both variables t and y, and is Lipschitz continuous. We've seen this before. in the y variable. So it only has to be Lipschitz continuous in y, not t. So I'll remind you of what that is. That if I plug in the same t value but two different y values, then that difference of f values must be less than or equal to some constant L times the difference in y values. Okay. So Lipschitz continuity is a kind of continuity, but it's a stronger form of continuity. It ends up, in other words, another way of putting it is partial of f with respect to y needs to be bounded. In other words, it's actually going to be less than or equal to L. So as long as that derivative with respect to y does not get out of hand, it can't like go off to infinity or anything. So if these conditions are satisfied, then the initial value problem, which I will abbreviate IVP, is well posed. So that's all it takes. Okay. So we're just going to be looking at an example. Most differential equations that one will come up with would be well posed because you're only looking at like a finite interval in time, and things can only go so badly, so quickly. Although I will give an interesting example of a ill-posed problem. Okay. So an ill-posed problem is, as an example, is y prime is equal to y raised to the 1.1 power. Now, if this were a class just of regular differential equations like Math 285, I would go ahead and solve this. This is some problem that can be solved. It's called a separable equation. But I'm not going to go ahead and do that now. But if I were to do that, you could show that there exists some time t, actually I'll call it t star, such that the limit as t approaches t star of a solution y of t is infinity. So in other words, there's a finite time at which the solution blows up. In other words, a vertical asymptote. This problem, I actually saw it in a calculus textbook I used long ago. And in that book, it was called the Doomsday Equation. And the reason it was called the Doomsday Equation is a rather silly one, because y, in this case, would refer to population of rabbits. And this equation would show that the population of rabbits would, at some finite time, become infinite, and you'd have doomsday because you'd have rabbits everywhere. Okay. Yeah. So, okay. So that's an example of an ill-posed problem. Now, a well-posed problem. Like in some cases, it's actually pretty easy to tell that a problem is well posed. Okay. Oh, okay. Let's see. So I'll just make one up. Y prime is equal to 2y plus 3t squared, something like that. Something that could also be solved using the techniques from Math 285. Now this right here, the right side, is your function f of ty. Now, from these kind of functions, they're polynomials, so you can tell that f is definitely continuous in both variables. But if I go ahead and look at partial derivative of f with respect to y, what is the partial derivative of that right side with respect to y? Yeah, it's just 2. Well, this is definitely bounded.
Yeah.
So this is a well-posed problem. So in a case like that, where you go ahead and take df dy and show that at least for a finite interval in t and in the whole real number line in y, that it's bounded on such a domain, then you're good to go and it's well-posed. Now, in some cases, it may be more difficult than that, but that's the general idea. Okay. Now, because I realize that not everyone in this room has taken differential equations. Sorry. Okay. But fortunately, and those of you who have taken differential equations and have forgotten everything, so it's okay. Because in fact, all those techniques you learned for solving differential equations in Math 285 or equivalent class, we will not be using any of them here. And besides, it was a while ago, but I taught it anyway. Okay. So in a differential equations class, well, I guess not like the one you all took last semester. Well, you didn't, right? 605. Yeah, I know you did, and you did. And I guess some of you will take that in the fall. Yeah. So in that case, that's all very theoretical, and you don't really. So we don't need any of that knowledge either. So, okay. But in an introductory differential equations class, the whole idea is you find a formula for y of t that's the solution of this initial value problem. You can do things like showing it's separable, or you use an integrating factor, or methods of undetermined coefficients, things like that. We're not going to do any of that because all those techniques for solving differential equations only work for differential equations of a very limited form, like certain special cases, like it has constant coefficients or something like that. The whole point for numerical methods is we don't have those limitations. We don't have to worry about them. Whatever differential equation anyone can describe, we just go ahead and solve it. So we numerically solve initial value problems by time stepping. Okay. The results of time stepping is not a formula of y of t. We love to have that if we can get it, but instead what we get is y1, y2, y3, and so on. And each one of these is an approximation of y of t1, y of t2, y of t3, and so on. So in other words, instead of our output is a list of numbers that represent the approximate solution at select times t1, t2, t3. And t1 is equal to your initial time, t0, plus some value h, which is called a time step. Some books use delta t, but for some reason people like to use h. I don't know why. And then t2 would be t0 plus 2h, and t0 plus 3h, etc. So h is just, so in general, h is just a difference between two consecutive times. So if we look at the ty plane, here's our initial time t0 at which we are given the initial value y0. So what I've plotted so far is just the initial condition. Okay. So from there, we have selected times T1, T2, etc. that just have a uniform spacing h in between. Now, that's what we're going to deal with because we're covering this chapter in a rather abbreviated fashion. But real time-stepping methods, like in actual mathematical software, would vary the time step. Like if we decide that we need to shrink it for more accuracy, or maybe we can lengthen it for more efficiency. And that is covered in the book. We're just not covering that section. So time-stepping methods would compute the solution at these times. So this would be y1, y2, y3. And now once you have all these solution values, if you want, you can fit them to a curve to describe a solution elsewhere. But really, these dots, this is what your time-stepping method is going to compute. Okay. So what we're going to see are various methods for computing those solution values. We'll start off with the simplest one to understand, and then realize that, oh, this is a slow and not so accurate method, so we need to improve it. Okay. Why is someone calling me?
You should
Okay.
tell him you're busy.
What?
Tell him you're busy.
They're probably trying to get me to like
Why the hell are you calling me?
refinance
That's
my
what you
house
say.
or something. Okay. Now, okay, so what I want to do, okay, 25 minutes, so I can at least cover the simplest time-stepping method, and I may be able to also prove that it works. Okay, so what I'm going to do is so the simplest time-stepping method is called Euler's method. And I rant about this in every class where his name comes up. It's an obligation. It is Euler, not Euler. I'll never forgive the actor Sasha Alexander from a series Rizzoli and Isles who referred to Euler's formula on national TV to release the 3 most important numbers in mathematics when it's actually the 5 most important.
I want to say that they pronounced it correctly in Hidden Figures. So.
Okay, well at least somebody did their homework. Like
How do you say it?
Euler.
Euler.
Oiler?
Yeah.
Oil?
Oil.
Oh, okay.
Yep. All right. We should put that in the oral final.
Say this word.
Okay. So what we do is Euler expansion. Sorry. Of the exact solution y of t, where the center is t sub n. So my general formula for Tn would be the initial time plus n times h, which you can see that that's a pattern over there. And I want to describe the solution at time Tn plus 1. So solution at time Tn plus 1 is equal to the solution at time Tn plus y prime at Tn times the difference in these two times. And then I'll just take it out one term more. So 1/2 y double prime at some unknown point, squiggly, times the difference in time squared. Now, the difference in time, so is just h. That's our time step. So I can fill that in here. And also y prime is f. So this is just h. So therefore this is h squared. So I'll have h f of Tn y of Tn plus h squared over 2 y double prime at some unknown point. All right. So, if we don't keep in mind that all we have of y is an approximation, and we go ahead and neglect this term, because we don't know what it is anyway. So this leads to Euler's method. Yn plus 1 is equal to yn plus hf Tn yn. And this applies for n equals 0, 1, 2, and so on. So that's it. That's the whole method. So you start at your initial time, t naught, and you have your initial value, y naught. So you'll plug those both into f. That basically gives you your slope. And you add this on to get y1. Then you use that over here to get y2. You just keep going. And you keep going until you reach your final time. Because you're starting at t naught, and you go all the way up to capital T. And compute that many values of the solution. So one of the problems from this section is to write a function for MATLAB function for Euler's method, where you're just going to have a for loop, and you'll just carry out this each time. Okay. So any questions on how Euler's method was derived? Yeah. So plug in the f, add, get a new value, plug that in f, add, so on. Just keeps going. Okay. Now, in the last 25 minutes, no, 20 minutes, sorry. What I'm going to do is do some convergence analysis, actually show you that as h goes to 0, because as h goes to 0, these values that we get should converge to the exact solution, because this is all I'm neglecting. So as h goes to 0, what I'm neglecting here is also going to 0. So you would think that as h goes to 0, because remember, y sub n is an approximation of the exact solution at time tn. So these should converge to these as h goes to 0. But I need to actually prove that. Unfortunately, this is a simple time-stepping method, so it's not terribly difficult. Okay. All right, so what I'm going to do is I'm going to define the error after n time steps to be the approximation minus the exact. So this is the error at time tn. Okay. Now, if I take what I wrote over there, I have the method itself, yn plus 1 is yn plus hf of tn yn. And then I have my exact solution. So I fill in my Taylor expansion. Plus, and then I have my a neglected term from a Taylor expansion. Okay, so what I'm going to do now is I'm going to subtract these two equations. Now, here we have approximate minus exact. Well, that's the error. So this is en plus 1 on the left side, because it said time tn plus 1. Here we have exact minus approximate again at time tn, so that's en. Now, here I have h. I'll factor out the h, and I have a difference of these f values. And notice the t values are the same. They're both tn. The y values are different, because here we have the approximate, and here we have the exact. And then I'm subtracting this off. Okay. Now, I'm going to make a couple of assumptions going forward. First, I'm going to assume that f is Lipschitz continuous. In the y variable, which I want to assume anyway to guarantee that this is an well-posed problem. Ill-posed, none of this is going to work. All right. The second assumption is that y double prime is continuous on the interval from your initial time t0 to your final time capital T. And what that lets me do, because a continuous function on a closed interval like this one, just square brackets, has a minimum and maximum. So therefore I can say that y double prime in absolute value is bounded by some constant m. All right. Now, these assumptions will allow me to simplify this, because I'm going to take absolute values of both sides. So I have en plus 1 absolute value is less than or equal to absolute value of en plus h. Now, here we have a difference in f values. That is less than or equal to the Lipschitz constant, L, times the difference in y values. But the difference in y values is approximate minus exact. That's the error at time tn. So I have en again. And then over here I have, taking the absolute value of everything, so it's h squared over 2 times m, because I have less than or equal to here. So now I have this relationship between the old error and the new error. So, the old error gets amplified a little bit. It's multiplied by 1 plus HL. But then we have this other term thrown in here, which could present a problem. But fortunately, this term goes to 0 as h goes to 0. So hopefully it won't get out of hand. So we have some error accumulation over all the time steps, but hopefully nothing bad. So here I have this relationship between new error and old. But what I want to do is get a relationship like what is the error at any time tn without relying on the previous errors, because this is really cumbersome. Okay, so what I'm going to do is I want to try to get a simpler relationship for the error from this, because this right here is actually a recurrence relation, because it shows how each error depends on the previous error. So I want something that's called closed form, where I could say, what is en without knowing the previous errors? So what I can do with this is I can write en in terms of en minus 1. I can rewrite that in terms of en minus 2, etc. And you're going to see a pattern emerge. And that will lead me to a closed form expression. Okay, how am I doing on time? 12 minutes. All right. I could do this. Okay. Now, so if I have En plus 1 less than or equal to 1 plus HL En plus h squared over 2m. Sorry. So now what I'm going to do is I'm going to rewrite this En in terms of En minus 1. So that's the same kind of relationship. 1 plus HL En minus 1 plus h squared m, or h squared over 2m. Alright, so this became everything here in square brackets, and I still have this sitting out here. Okay. Now let's simplify. 1 plus HL squared En minus 1 plus h squared over 2m times 1 plus 1 plus HL. Now, I'm going to go one more, and that will make the pattern clearer. Because now En minus 1 I can rewrite in terms of En minus 2. Which only takes like 3 or so to see what the pattern is. En minus 2 plus h squared over 2m times all the other stuff. In fact, there's a reason why I could have combined these to get 2 plus HL. That would actually obscure the pattern, so that's why I didn't do it. The great computer scientist Donald Knuth said premature optimization is the root of all evil. Now that's for programming, but you can say that something is true in math. Premature simplification is a problem. All right, so now I can combine these. So I have 1 plus HL cubed En minus 2 plus, and then I have h squared over 2m times 1 plus HL plus 1 plus HL squared. So now we have an idea of what pattern is emerging. That you're going to have a power of 1 plus HL in front of the error, and over here you're going to have h squared over 2m times a sum of lower powers. Ah, dang it. Okay, well, class is almost over. So.
Okay.
I'll just hope that everything is recording, but it should be. Nah, fine, put in your password. I'm paranoid.
Yeah. You don't want to end up doing it twice.
Well, at least there's only 8 minutes left in class, but still. Okay. Thank you. Okay. Yep, still going. So in general, we have En is less than or equal to 1 plus HL to the n times the initial error E naught plus h squared over 2m times the sum going from 0 to n minus 1 of 1 plus HL to the I. So that's a geometric progression. Now, but the thing is, E0 is the initial error, but that's 0 because we're given the initial value. So we can ignore that. So this is all that's left. Now, there's a formula for the sum of a geometric progression like this one. So I'll fill that in. And that would be 1 plus HL to the n. So it's the maximum power plus 1 minus 1 all over 1 plus HL minus 1. Okay. So in general, So partial sum of a geometric series, which will bring back fond memories of Cal 3, I suppose. Okay, there's no such thing as a fond memory from Cal 3, but 1 plus r squared up to r to the n is equal to r to the n plus 1 minus 1 over r minus 1. So that's the formula that I use down here. Now, the ones down here cancel, so down below you only have HL. But that H cancels with one of the H's up above. So what I can do is say this is less than or equal to HM over 2L times what's left is this 1 plus HL to the n. I can say that's less than or equal to e to the HLN minus 1. But n times h is equal to Tn minus T naught, which is less than or equal to capital T minus T naught. So I can go a little further. I know this is bad board usage, but deal with it. So my final expression for the error is Hm over 2L e to the L capital T minus T naught minus 1. So the error at time Tn is less than or equal to that. Now, whoops, sorry for those of you watching, although there's hardly any of you left. Actually, I think we only have one remote student now. Well, but again, we have people missing who should be here today. Dang it. Okay, well, hopefully we're all... No, I'm not going to say that. I was going to say hopefully we're all sick, but that's a terrible thing to wish on someone. That's not what I mean. If they're not here, hopefully it's because they're sick and not some other reason. Yes, we'll go with that. All right, so they better be watching it. Okay. Now, how does this expression help us at all? Okay, I'll continue with bad board usage and fit everything over here because I have practically nothing left. Okay, I'll just separate this here. Okay. So what this means is as h goes to 0, En, which is the difference between yn minus y of tn, also goes to 0. So in other words, the limit as h goes to 0 of the maximum of the over all n under consideration because for any given h, n will only go so high. The maximum n you could possibly have is capital T minus T naught over h. That's how many time steps. So the difference between the approximate and the exact over the whole time interval, that difference goes to 0 as h goes to 0. Because it's true for any time at all that you can have. So it's true in general. So what we could say is that Euler's method is convergent. Now, this is a formal definition of convergence, that as h goes to 0, the maximum error over a whole time interval goes to 0. Now, informally, so therefore, intuitively, what it means is the approximate solution that is all these yns converges to the exact solution, which is y of tn for all the different time for any tn in this interval. So these values, these y values that your time-stepping method is spitting out, if you were to connect the dots, that would actually equal y of t that you would get if you were able to solve your initial value problem exactly by hand. So that's good. This method actually works. So if you keep shrinking h, you would see your solution getting more accurate. Now, Euler's method is still not a very good method because the error is proportional to h, whereas we will see methods where the error is proportional to a power of h squared, h to the fourth. So the error will be a whole lot smaller. But this is a start. So by tinkering with Euler's method and seeing how we prove a method works, we learn how to do the same for more sophisticated methods. So yes, I know I'm out of time. But actually, I've made some good progress today, so I won't have to cover as much on Thursday. So we will start looking at more sophisticated time-stepping methods starting on Thursday. Okay.